Hi, in these 1E energy level diagram notes, our objective is to learn how to read and label an energy level diagram and to understand how it changes with a catalyst. Here's a quick review of the collision model. This is how we know chemical reactions take place on a molecular level. We know that the rates of reactions are affected by both concentration and temperature, and that's because in order for molecules to react, they have to collide with each other. And they have to do so with the right orientation and the right amount of energy. Here you see an unsuccessful collision. We don't have the right speed. Here we don't have the right orientation, unsuccessful. Here we've got the right speed and orientation, so we've got a successful collision. We do know that the greater the number of collisions, the faster the rate. So it would make sense then that the more molecules we have present, the greater probability of collision, and the higher the temperature, the more energy is available for those molecules. They're moving faster, and the faster the rate. Most collisions actually don't lead to products. In fact, a very small fraction of them do. Here you see an unsuccessful collision. In order for a reaction to occur, the reactant molecules, again, must collide with the correct orientation and with enough energy to form products. Activation energy is the amount of energy required to initiate a chemical reaction. Remember that in order for a reaction to occur, we have to break the bonds in the original reactants, and breaking bonds requires energy. Here's an energy level diagram showing the energy change during the rearrangement of acetonitrile. Notice here this methyl group is single bonded to a nitrogen, which is triple bonded to a carbon. And during this chemical reaction, this nitrogen and carbon actually switch places. But in order for that to happen, this single bond between the carbon and the nitrogen has to break. And that requires energy for this bond to break. And so that's what this activation energy is that you see here. Once that bond breaks and a new bond is formed between these two carbons right here, a lot of energy is released, and we have our new product down here. An energy level diagram is simply an illustration of these changes in potential energy as we go from reactants to products. The reactants are always found on the left-hand side of the energy level diagram, and the products are always found on the right. This peak right here is called a transition state. Sometimes it's also called an activated complex, and that's where we've got a very unstable intermediate between the reactants and the products. The difference in energy between the reactants and this activated complex right here is called the activation energy. It's denoted by this capital E with a subscript A. And the difference in energy between the reactants and the products right here is considered enthalpy, energy change, and it's often depicted by a delta H or sometimes a delta E. Exothermic reactions, as you may remember, are hot. They feel hot, and that's because the system that we have is losing energy. So the energy of the products in an exothermic reaction will always be less than the energy of the reactants. And this difference in energy right here is the energy that leaves the system. So excess energy is released in the form of heat. The reaction feels hot. This delta H or enthalpy value is calculated by taking the energy of the products and subtracting the energy of the reactants. So it will be a negative value for an exothermic reaction. Endothermic reactions are the opposite. In an endothermic reaction, the products have more energy than the reactants. They feel cold because the system had to gain energy from the outside. Energy has to be pulled from the environment. Delta H in this case, or enthalpy, will be positive because the energy of the products is greater than that of the reactants. The role of a catalyst in a chemical reaction is to speed up the rate of a reaction, and it does so by lowering this activation energy, or this energy requirement to get to the activated complex. It provides a different reaction pathway. There's a lot of science behind catalysts, and we're just scratching the surface. But at this point, you just need to know that they speed up a chemical reaction by lowering the activation energy. Very briefly, there are two types of catalysts, homogeneous and heterogeneous. Homogeneous catalysts are those in which the reaction and the catalyst itself are in the same phase. They're both liquids or both solids or both gases. And heterogeneous, it's the opposite. The catalyst and the reactants are in different phases. For your assignment, you'll need to be able to read an energy level diagram. So I'll give you some examples. This says how much energy is needed to get the reaction started. That's basically asking you what's the activation energy. So the answer to that question would be right here, 134 kilojoules. The second question says how much energy is needed to get the reverse reaction started. In the reverse reaction, we're going in the opposite direction. So that would be the activation energy for the reverse, which would be the difference in energy between the products and that activated complex. That would be 360 kilojoules on this diagram. In this last question, we're asked how much heat is given off during this reaction. We're asked for the enthalpy. That's the difference in energy between the products and the reactants. It's a negative value, and there it is, negative 226 kilojoules. In this next example, we have a catalyst. Here it is. First question, what does a catalyst do to the rate of a reaction? It increases it. Number two, because a catalyst creates an alternative reaction pathway, how does the new activation energy compare? Here we can see that the activation energy is lowered when we add a catalyst as compared to the original. How is the activation energy of the reverse reaction affected due to the new reaction pathway? You can see the reverse reaction, the activation energy is also lowered. Finally, how does it affect the delta E or delta G on this graph? That's that enthalpy, and you can see it's completely unaffected. The difference in energy between where you start and where you finish remains unchanged if you add a catalyst. One more important note, if you change the temperature of a reaction, the only way it's going to change a graph like this is it's going to shorten the period of time it takes to get from the reactants to the products. So this will cinch in a little bit here. It doesn't change the energy of the reactants or the products because that energy is potential energy held within the bonds of that molecule. It's not the it's not the kinetic energy that we're graphing here, it's potential. It also doesn't affect activation energy. So again, changes in temperature don't affect anything on this graph other than the amount of time it takes to get from reactants to products.